ended up deciding that printing on the VGA console was too complicated. Like in itself, it's not that complicated, right? Uh, but there is something simple that we can do, and not only it is simpler, it also allows simple input. And the VGA screen, like, is not a keyboard. We would need to write another driver, a much more complicated driver for the keyboard. So today, our main objective is to print stuff on a serial line. And so we're also going to change. We're going to start with changing the script so that we have a serial line device. So Metal Snake is here with me, and normally the audio is correctly set up. Shouldn't be too loud. So tell us, guys, if there is anything wrong that we need to know. And here I'm just looking for the option to have a serial line. And I probably could copy it from another script I have. Yeah, it's usually something like this, and I guess there is a shortcut like that, yeah. So this would be serial, and it would probably have stdio here, yeah. Now you can see, and this is purely a QEMU thing, you can see that the monitor is already using stdio, and because of that, QEMU is not going to be happy. So we're going to disable the monitor, just so that you remember the monitor. Oh wait, it's still starting. Yeah, it's still starting the VGA console. We're going to disable it like this. No graphic, if I remember correctly. Okay, it's this option here. Cannot use stdio. Okay, so there is a monitor by default that we need to change apparently. Monitor none. Now this means that here what we have is the serial console. Now it doesn't print anything. We have no output, so it's pretty normal that nothing is happening. But we have a combo to access the monitor normally, which does not work here. I wonder I wonder if it's VNC. Let's try more things. No, it doesn't work. So we need to set up that first. I'm surprised that the monitor doesn't want to work, so I'm gonna check how it's done again. As you would do with a real project, by the way. And you would probably find something on how is it called? Stack Overflow. Okay, I have nothing here. So how do I do that? Oh, maybe it's just no graphic, actually. Should be enough. Okay, there we have it. So I have a key combination, which is basically Control A followed by C, which allows me to have the monitor somehow multiplexed with the serial console. So here I can type commands, get information about registers, etc. And go back to the serial device, which currently is completely not handled. Okay. One thing I wanted to do before starting. So are you here, Metal Snake? Can you hear me?
I can hear you, yes.
Okay. The first thing I wanted to start with actually is the license. That's something we forgot last time. It's not really.
Oh yeah.
It's not really that we forgot. It's really that we had priorities. But when you start such a project, like even a small open source project, the license, like for me and other people, the license matters. Now we have to choose what kind of license. Are you familiar with the major ones?
Name wise, yes, not so much as what they really entail.
Okay, so basically GPL, MIT, BSD, that kind of
Mm-hmm.
things.
Yes. Yeah.
Okay. So I think I think that too is an interesting subject for students, and I'm going to talk about it very quickly. There are basically two sides of open source, and actually the whole doesn't have a name because each side has a name. You have open source, but you also have free software. Free software is ideological, whereas open source is purely pragmatic. Open source is concerned about technical quality, while free software is concerned about your rights, basically. And along with them, you have two types of licenses. One is the GPL, the GNU generic, the General Public License, sorry, which was written by the FSF, the Free Software Foundation. So this one is on the free software side, um, and the major thing that you should remember about it is that if you use the GPL for your projects, you basically prevent people from making the code proprietary. So by making it GPL, they have to make public their own modifications, and many companies are annoyed by that, especially the GPL v3 because this one goes even further. The GPL v3 says that if you use GPL v3 covered software, you have to provide the means to the users to change the software. So basically, every distributor or constructor of embedded devices who want to sign their firmwares cannot use GPL v3 software because of that. Because otherwise, they would have to provide keys like developer keys. Some companies do. Some companies do provide developer keys and are compliant with GPL v3, but many just don't want the burden. So that's one detail. Then you have the other side, which are called permissive licenses. And this one is usually, like, it's not always a rule, but it's usually associated with open source, quality focused projects. Um, and the main ones are the MIT license and the BSD license. Currently, and I think it was a move, yeah, I had to do that recently with one of my projects. I moved it from the BSD to the MIT license because on GitHub, for example, the licenses are considered so close that there is no reason to have two. So GitHub decided that they would only know about the MIT license and forget about the BSD ones. So we have to choose. Do we make it annoying for people who want to make it proprietary, or is it completely permissive? Now, usually the choice is very simple. If you have something of value that you want to prevent others from making money too easily with it, you go with the GPL. And again, it's not really about money. It's just I'm just giving you one way to think about it. There are other ways to think about it, but a lot of like many times when the GPL is used, it's really because the GPL covered software does something that many other um, alternatives or competitors actually don't do. So the idea is to prevent them from achieving the same thing too easily. Because if you're not free software, why would you just um, like benefit from free software? The reasoning of free software is that every software should be free. So if you don't have, like, if you don't make free software, it should not be easy for you to get what people work for in the free software community. Whereas for open source, the reasoning is completely different. Uh, the dogma, it's almost a dogma, but it happens a lot of like it's really, it's dogma, but it's almost a rule statistically that when software is free, uh, it's naturally better. And the reason is because people can contribute, find bugs, fix them themselves, etc. So then you make you use a permissive license if you think this way. So here it's an educational kernel. We can't really say that we're doing something others don't. On the contrary, it's meant to be simple, easy, and as an introduction to more complicated things. So we're not going to use the GPL because of that reason. Uh, Now I have a small problem with authorship, but it's going to be easy to fix it. Let's reuse that template here, 20 lines. So it's 2017. Okay. Now I'm gonna, yeah, I'm gonna need your name too here, unless you don't want your name to appear here.
You can use my name. That's fine.
Okay. We could make the make file, but it's not usually. Uh, it's too small to deserve such a license. Or to deserve. It's not really deserve, but like there is no real point. Oh, I didn't change before copying. That's fine. We can change that easily. There are not too many files. That's all, I think. We only have 3, right? Okay. There you go. And we'll need a
No
copying
problem.
file too. Oh, it's Vim.
Yeah, hang on.
Wait.
Okay,
Stop,
I'm
stop,
not
stop.
touching anything.
Go ahead.
There we go.
Okay, and I'm going to copy that. So, um, the boot file. Then we have the definitions. Wait. And then, why am I closing this? Main is what we have open. That's all, I think. Okay, for now that's all. Okay, so this is the only change we have. Let's commit that immediately. Oh wait, I forgot something. And I have other changes apparently. Oh, yeah, I want to reset that. We need a copying file. Okay. Now this is out of the way. Alright. Now that this is out of the way, we can really focus on the true work, which is the UART driver. We're going to do that in 2 parts. The first part is going to be me writing assembly functions to access the registers of the UART device. The second part will be Metal Snake writing the C driver using the functions I have written in assembly. Okay, so one thing to know about the UART on x86 is that it's not memory mapped. It uses what is called I/O ports. And I/O ports are like an address space. So basically, it's almost like if you had memory and would address it, except that it's not memory, it's instructions. So we're going to take a look at them. and really only one right now, which is going to be out. Output to port, and you have another instructions which is named in. So that instruction here takes an 8-bit value and writes it to a 16-bit port. And you have all these variants to write your data. So um, that's what I'm going to write in assembly. I'm going to use a separate file. So let's have a template. I'm going to call that IO. Immediately add it to Git so we don't lose it. Oh, that's right, the keyboard doesn't work well. Like, because of VNC, some things like repeating sequences is not easy to do. I'm going to name the function IO. How are we going to call it? It could be write byte. It could be just write. Let's call it write. So the section is text. Actually, it's .text. Code is by default 32 bits, but we could write it as well here. Let's again use put s as a template. Okay. And this function should be made global. And by the way, start here should be made global as well. It's actually weird that it works without that, but I suppose the linker is smart. If you don't export a symbol, that's something interesting to look at. If you don't export a symbol, it is normally not available to to the other compilation units. Makes the symbol visible to LD, to the linker. If you don't do that, the symbol remains local, as if it was declared static in C. So I'm surprised that it worked, but there is some detail that we don't know here. Okay, now the interesting thing is not really the out instruction. Like, I'm just going to copy one of these. Probably not this, because it won't be an immediate value. It will be passed by the user. So it will be one of those, and probably this one, because we want, like, we have 16-bit support. They can't be, wait, normally they can't be 32 bits. So it's just the operand size. Whatever the operand size here, the value of the port cannot be greater, like cannot be more than 16 bits. So I'm probably going to use this. One reason to use that form is if your arguments already come in that particular register here. Output double word, or maybe it does output 2 words. That's weird. I don't think that's possible. Well, it's possible. I mean, the processor can do it, but the rest of the hardware normally doesn't. Hmm. Anyway, we won't be using anything else than 16 bits. No, but what the interesting thing is how we communicate with assembly from C. Right. So we're going to do it in 2 steps. First, we're going to pass arguments, and then we're going to return a value. If we need to return a value, do we need to return a value actually? Not here. IO read would need to return value, but not write. Okay. And in order to understand how C communication between functions occurs, we need to look at what's called the calling conventions. The ABI. It's part of the ABI. So here you have the System 5 application binary interface, which is basically what's used on all Unix systems, System 5. And then we have the specific version for the Intel 386, which is what we're coding for. We are not making a 64-bit kernel here. Now, this document is old, it doesn't have a table of contents, and apparently I'm already right where I want to be. Function, calling, sequence, registers, and the stack frame. So yeah, we have a number of registers, etc., etc. Here is a list of the basic registers. We're going to completely ignore the floating point ones because we're not doing floating point in a kernel. Normally, kernels are not used for that. Some can. I mean, if you have applicative code, or if you really have code that is meant to use floating points in the kernel, why not? But on x86, it's even harder because using the floating point unit involves more context, more state to save. So usually it's only in user space. We're going to focus on this. So basically we have those three registers. You'll note that EBX is not here. EBX is reserved. You'll see that later. These registers are like generic registers. The compiler can allocate them for basically anything. The reason why you have a specific usage here is not because of the compiler or the ABI, it's really because of the processor. So for example, if you look at the processor manual here, you're going to see specific registers. Like you can't use other registers. This single instruction here, this single opcode, encodes the whole thing, including the registers. And many instructions are made this way. And so, for example, when you multiply or divide, you're going to have those registers used by default, whether you want it or not. So that's one thing. Hello, Agustina, by the way. But that's really the processor. It doesn't mean that you cannot use the registers for anything else. It only means that if you use divisions, or if you have like string functions using a counter, those registers are going to be used implicitly. That's it. That's not the case for the other registers, especially ESP, which is a stack pointer. So you could use the stack pointer for what you want. It's a register like any other. You can add, you can multiply, divide, that's fine. But you can't really mess with the stack pointer, because if you do that, you don't know where your variables are, you can't return to the caller, you can't do much. So the stack pointer is pretty much reserved. ESI and EDI are normally used as source and destination indexes. But that's the same as those ones. You can use them for anything, really. And here, for example, they are used for local register variables. Why not? It's obsolete, really. It's the register keyword as it was used and implemented 20 years ago and more. Same for EBX. BP is quite interesting. You can see that it's optional, and it really is optional. But it's usually used as the base pointer. So what they call here the stack frame pointer. Remember, when you call a function, the function creates a stack frame for itself to store local variables when it needs to like when it can't store everything in registers, it needs to swap some of them onto the stack. And you really only need the stack pointer for that. But for convenience, especially when tracing function calls, it's quite convenient to move the value of the base pointer directly into the stack pointer to destroy the current stack frame. So imagine, remember, usually stacks grow downwards. So imagine EBX is like 10, and ESP, not EBX, sorry, EBP is 10, ESP is 5. So you have 5 bytes for your local variables, and this is bullshit. I mean, it's not real, right? Addresses are going to be aligned and much higher usually, but it's an example. You have 10, 10 at the top, 5 at the bottom, and by moving the value of EBP into ESP, both are 10. So you basically erase or suppress, maybe, uh, unwind is the exact word. You unwind the stack frame this way. You you basically go back to what it was, and from there you find the return address, so the address to jump to in order to return to the caller, and this way you can trace function calls. So that's quite important to know. There are alignment issues on the stack pointer. The stack is word aligned. So here, a word is defined as 32 bits. You can read it earlier in the document. Uh, Basically, that's it. The stack pointer needs to be word aligned, which means that its value must be a multiple of the word size. That's all. And it's important because when the compiler generates code, it is going to assume that the stack pointer is actually aligned to word boundary. And if it's not, you might have, like, on some processors, it might just crash. On the x86, it's going to be slower. Quick question, just for the hell of it. Are there any particular sites you use for reading academic papers? No. And Agustina could tell you the name of a good one, which I can't remember it. I don't use it often enough to remember it. That's sad. But there is one for students who is quite good, but I forgot the name. Okay, so here several key points about the stack frame. Word align. Argument words are pushed onto the stack in reverse order. That is, the rightmost argument has the highest address, so is pushed first, preserving the stack's word alignment. ResearchGate. I don't know about it. I just use Google until I find what I want, basically. An argument size is increased if necessary to make it a multiple of words. This may require tail padding depending on the size of the argument. So, also that's quite important. If you have argued sometimes with people about passing around uh, fixed width integers, like an int 8 or an unsigned int 16, you know, uh, usually the calling convention optimizes this by using a full word for passing your argument. So you can use them all you want. It's not going to affect the performance of your code, like almost never, only in tricky cases. And if you want to make sure that's the case, just check the generated machine code. An argument size, so yeah, that's it. Other areas depend on the compiler and the code being compiled. The standard calling sequence does not define the maximum stack frame size, nor does it restrict how a language system uses the unspecified area of the standard stack frame. Okay, so that's a few points to keep in mind. Now we're going to the registers. Okay, all registers are global, yeah, and thus visible to both a calling and a called function. Registers EBP, EBX, etc. belong to the calling function. Okay, so what this means is that if you call a function, you cannot expect those registers to have the same value they had when you called the function on return. Their values may have changed. So if you had some values in them, you'll have to reload them into the registers. That's what it means. So yeah, in other words, a called function must preserve these registers, the values for its caller. Wait, okay, it's actually the contrary. I read that badly, sorry. Belong to the calling function, so it's the caller, not the called, not the callee. So those ones will be preserved and the other ones will be changed, and you can't know, you can't rely on their values, but these ones you can actually. Starting well. Uh, Remaining registers belong to the called function. Okay. Some registers have assigned roles. So yeah, we talked about the stack pointer, the frame pointer, integral and pointer return values. So this one is used when you return an integer or an address, which is also an integer. EBX, the global offset table base register for position independent code, we can completely forget about that. We're not using position independent code, you're not generating position independent code, we don't care at all. So this one, we don't care about it. But still, we're going to save it because that is the calling convention. Now, you can change the calling convention with compiler arguments. For example, you have f emit frame pointer. This one basically turns EBP into a regular general purpose register. And you have others, like maybe there is one for EBX. I remember there was one. Control how many registers are used to pass integer arguments. By default, no registers are used to pass arguments, and at most 3 registers can be used. Okay, so this thing changes the calling conventions. And it basically uses registers to pass arguments instead of the stack because it's faster. You don't have memory accesses. But it also means that you're not going to be binary compatible with libraries and well, other functions. So for example, if you write assembly code like I'm about to do, and you use this option with the compiler, you cannot assume, you cannot know how the compiler is going to pass these registers to you. This is like an internal calling convention that you cannot rely on. So you would have to declare those assembly external functions in a way that tells the compiler, don't use your optimization when calling them. I think there is a compiler attribute for that. I don't remember exactly which one. And this normally, I guess this uses EBX. It's not specified here. I would have to look that more into details. But basically, that's what you need to care about when writing assembly code that you want to interface with C or other languages. So my arguments will be um, the byte to write, word and double word. I've never used these things, and it's really weird that it's the same opcode. Anyway, one argument will be the byte that we want to write, and the other one will be the IO port address. So yeah, DX, this is 16 bits. When you see AL, this is 8 bits. When you see AX, it's 16s, and when you see an E, which means extended, I think, it's 32 bits. And when you see an R, it's 64 bits. Right, so let's write the prototype in C just to have actually, I'm going to write the header file immediately. The function will be void IO_write. Let's say that we write to port first, so port and then byte. Okay, so arguments are pushed in reverse order, which means I'll have the byte first and the port next. Okay, and actually, you know what? Let's just no, they're on the stack, right? They're on the stack. So let's load them. To load them, I'm going to use mov. As usual, it's the go-to instruction in x86 when you move things around, memory, registers, immediate values, whatever. Hello load, good evening, welcome. So mov, I'm going to load a whole word because the the calling convention said that normally arguments are passed in whole words, and I expect my word to be like the most significant bits should be 0, but it doesn't really matter because we can just use AL afterwards, which tells the processor to only use the least significant 8 bits. So, have you decided yourself if you're going to host a past recording on Twitch or something else? I told you they're going to be highlighted, and if that's not enough, I'll put them on YouTube. Hello, local hoster. Hello, the mushmouth. Hello, everyone. So, moving from um, from some reference, we're going to see which one, to registers. Basically, what I want to do is move what I have on the stack to those registers. The first one is the byte, so I'm going to put that in EAX, but what I need to know is the location in memory on the stack. And that's pretty easy. I don't have local variables. I really don't have much. The stack currently points right after the return address and has nothing else. So I can just use ESP like this and store that in EAX. Now, I need an offset here because this actually points to port. Port is the last argument, so the stack points to the last argument, the last being pushed. So I'm going to need an offset for that one. And the offset is going to be 4 because words are pushed in, well, arguments, integer arguments are pushed in words. So this notation here takes the stack pointer, adds 4, so basically you look up and stores that in that register. And this one is going to go into EDX. And after that, I'm going to add an infinite loop so that we can check with the virtual machine. I need to add the files. Yeah, I need to add them to the to Git first and to the makefile. Why would you do it in C and assembly when there are other languages which haven't had an OS made? Because C is really good for that. It's an educational project, and even for a real project, I would use C. C is really good for that kind of things. One reason, especially for educational, for an educational project like this, is because C has no runtime. So you don't have to explain people why you are, for example, setting up thread local storage or whatever you need to do for your, I don't know, runtime to work. There is another streamer called White Noob who writes his operating system in D. And he acknowledges himself that it's a pain. It's a real pain for him to do that. It's just he admits that he does it in D because he likes D. That's all. But it's a pain. He himself calls it the hard way. I don't want an educational project to be hard. A Python operating system, maybe that's possible, but same problem. You need a runtime to work before you can even run Python code. So you'd need to do a lot of things just to make like your basic code run. In C, it's really easy. It's really quick. Okay, now I'm going to call the code from C. So we're basically here, we're going to remove that, okay? This is our stack, okay. No print function anymore. We're going to include, so yeah, let's move it this way. I want standard headers first. I separate them with an empty line to let people know that these are not standard, in case they wonder. Okay, so main now knows about IO write. The port is going to be 1234, and the byte is going to be AA. Okay. So let's take a look at our registers. EAX is 1234 and EDX is something else. So apparently I messed up. Why is the stack pointer not pointing to the last argument? Let's take a look with GDB. So registers, the stack pointer is here. Okay. We're going to use the X command, which is used to dump raw memory. The format is going to be a repeat count, so we just want 3 because we know we have an offset of 1. A format letter, hexadecimal, and the size is going to be word. So I can see my arguments, and then I can see this. Okay, this is the return address. So stupid me, I forgot that. The return address is pushed last. First, you push the arguments, and then you jump, you make the call. And we can actually check that with the disassembler. It's going to main. Okay, you can see that here. So the arguments are pushed in reverse order as mandated by the ABI, the calling convention, and then you have a call instruction. And the call instruction pushes the return address onto the stack and then jumps. So that's why we have this discrepancy. Easily solved. Okay, now we have the right value in EAX, and we are only interested in AL, really, and DX has the right port value here. So I can just write my out instruction. Now I suppose I'll have to give it a suffix to choose between these forms, although they all have the same opcode. I really don't get that, to be honest. Let's try without a suffix and see how it goes. Right, out. So this would be ALDX. Okay, and then infinite loop. By the way, these are completely bogus values. I don't want to write just anywhere. But it's a virtual machine, so let's just do it. Okay, seems to work in that we are where we are supposed to be here. We do have the right values. Everything looks fine. I'm interested in the generated code. Okay, so it's here. EE, and that's it. Oh, it's EE. Oh, it's EE and EF. That makes a bit more sense, although those two ones... Like, I understand how this one is now identified by the processor, but I don't understand the difference between those two. Still magic, but I really don't care about that. We could look for it, but we're just gonna waste a bit of time for nothing. Now we need to return. So it's quite easy. There is an instruction for that, which is ret. So ret does the reverse of call. It pops the return address and it jumps at that address. And we could really write it with a pop and a jump. But ret is better. You will see some functions. For example, can we see that here? Yeah. It's not exactly that. It's this though, yeah, it's partial. The reason we don't have the end is because of the infinite loop. The compiler knows the function doesn't return, so it doesn't write the epilogue. This is a prologue. The push here saves the base pointer of the previous stack frame on its stack, and then it creates a stack frame for itself by moving the current stack pointer to the base pointer register. So basically, imagine you had like from 5 to 10, like earlier, and then you're going to have from 5 to 5. Your current stack frame is empty. And then it's going to reduce the stack pointer. This is how local variables are allocated on the stack. So now ESP, for example, which was 5, becomes 5 minus something, let's say 2. So 5 minus 2 is 3. So you have a new stack frame from 3 to 5, for example. Here the value is 8. And yeah, like I said, my numbers are completely bogus because they're usually aligned and bigger. Just to give you an example. Okay. So the write function is implemented. Now, it's all good, and normally it works, and I'm pretty confident that it works. It could be written in inline assembly, but inline assembly is still, like, I don't think it's interesting to show it for students. They can learn that later. It's quite advanced, and many compilers just don't have good inline assembly, so it's better to have real assembly code and learn about calling conventions. Which means that my part is basically done.
In assembly, by the way, I've seen the red command. I've also seen leave used before red.
Oh yes, so that's what I was mentioning here. The function doesn't return and doesn't implement an epilogue. So the epilogue would be implemented by the reverse of this. And I think there is an instruction for that, which is enter. And leave is just the opposite. So it moves it moves the base pointer back to the stack pointer. So remember, we had 5 to 10. So moving the stack pointer to the base pointer means that, oh wait, maybe moving the base pointer to the stack pointer means that you have 10, 10, right? You basically destroy your stack frame and you're about to return. And then you have the pop EBP, which restores the frame of the previous function, so a value that is bigger, like 10 to 15, for example. And that's what leave does. And let's check actually. I'm pretty sure that there is both an enter and leave instructions. Enter. Okay. Now, why the compilers prefer to emit push and mov, I'm not sure, but they probably have a good reason.
Yep.
And then you have leave here, which does really the same thing, see? Now, yeah, you have those. It's a bit more powerful because it handles those cases where you might have different operand sizes.
Okay, yeah.
But it's really the same thing. So yes, you have a read instruction is commonly executed following a leave instruction to return program control to the calling procedure. Let's take a look. So it's 64 bits code, but I guess it works as well. Sometimes you will see that the leave is not where you think it is, and actually we need functions that call other functions for that to work, I guess, with optimized code. Because if your function is small, it doesn't really need a stack frame, right? So we need complicated functions. What's base here? Let's look for leave directly. Oh, maybe on 64 bits it doesn't exist anymore, or it's not generated by the compiler. Let's try and generate it in our code. Like, I'm going to remove that, rebuild, check the generated code. No, we don't have it. So here the compiler decides that it's not relevant to use that instruction. I'm going to disable optimizations and use O0 instead. Still not. The compiler knows that it doesn't need to do that.
Okay.
Well, knows
Well,
it determines that it's not useful here, despite having generated a prologue here. So that's weird. Yeah,
but you're not really doing anything after that, so maybe.
I don't know. This is leave actually. This is leave. It pops the base pointer. So the base pointer is restored to the value previous to the call, and then it restores the stack pointer by using a register here, which is the last argument, well, actually the first argument, and loading its effective address shifted by this offset. So it's basically leave, but the compiler decides it's better to write it this way. I'm not sure why, but I'm not
Fair enough.
surprised. I've seen it often. So wait a little, please. There is a Golang OS, but you have all these problems with runtime. Yeah. My OS I plan to make is in Golang. Really? Well, you'll show us. I'm interested to see how easy it is or hard to make a simple thing run. Like how long, how much effort do you need until the runtime is ready for that? You can't use basically nothing from the language. Yeah, that's true. You need to implement the lower layers that the language relies on before you can actually use the language. I might start writing my first OS in C to learn from it. Then do Golang when more experience. Why not? You'll see. You'll see how it goes. C might be considered dangerous and not powerful, but it's really good for that kind of projects. Okay, let's use optimizations again and actually reset the whole code. Okay, did I push the code? No, I didn't. Okay, so now this code goes to my personal repository and is mirrored to GitHub, which means that you can now retrieve it and work on it. So now we're going to work on the UART driver, and Metal Snake has control.
Oh wait, it's just git fetch, right?
No, it should be pull, but again, uh, by default you're pulling the branch you're tracking, and you're not tracking my branch, you're tracking your branch. So you need to pull another repository, and then you need to update yours. Do you want me to remind you about the commands?
Yes, that will be helpful. I
Okay.
don't use git.
So git remote gives you the remotes you have. This is the one you have. This is yours, and this is mine. You can use branch v, actually more v's, to know what a branch tracks. So your master branch tracks origin master, which is this one, on this repository. I've updated this one.
I need to be
So
pulling that one.
you need to pull from my repository, my remote first. So this is what you're going to have. One line, decorate, graph. Okay. So you're basically here, and you want to merge this. So you could merge or you could rebase. Rebase may change history, so it's usually not a good thing. Okay. Now if you take a look at your graph here, your local master branch is up to date, but the master branch on your repository is not. So now when you push, it's going there by default. And now everything is up to date.
Okay. Okay, so what we're gonna do is the UART driver now. And just could you open a
Yes, a browser?
yes, please, yeah. So what I was looking for was the serial driver, I think it is. Have the serial ports, that's the one. And this is basically the one we're going to be using. This is the base address of the COM port, I suppose. But before that, we need to set it up.
It is. It is. So one thing though, the PC architecture is messy, very messy. On some machines, that port is different.
Okay.
But we're going to use hard-coded values because it's simpler. It's actually what the virtual machine uses, and it's basically standard, so it's okay.
How would you go about figuring out what the exact port for that is?
You ask the machine with plug and play. So today that would be ACPI. You discover the hardware with ACPI,
All right. Okay.
and that's very difficult.
Yep.
Not very difficult, but completely out of scope.
Okay. So first you need to can I have a look at the example that you have in Exif?
Sure. So you can just use this. Okay, I'm letting you.
Yep. And I believe it was in here.
It's called UART, and we should do the same. We should make a file named UART for the same reason.
Mm-hmm.
You won't need nearly as many as much thing. Well, nearly as much code or definitions.
So we're basically adding this, essentially. This is what we're gonna.
Yeah, but I would not recommend. Like, I really don't want you to just copy that and go with
Mm-hmm.
it. I want you to understand what they are and only have them if you need. That's a very, for me at least, that's a very strong principle. Do not have things that you don't use. Everything that you
That
have
makes
in your
sense. Yeah.
project should be used.
Mm-hmm.
So until you know that you need it, don't.
Okay.
The usual routine is just creating the files, adding the licenses um, in your headers. And actually, I forgot that. Let me just, yeah, I'm going to fix that before you start. Sorry,
Sure.
completely forgot. Um, this is a header which has no inclusion guards.
Oh yeah.
Okay, do we have any others? We have the defs file.
Defs.
Yeah, same.
Yep.
We can let it like this, but there's no reason to have those spaces really. So you can write those macros here. You can have them as you want. You can add underscores at the end or only at the beginning. It doesn't really matter as long as you're consistent. Okay. Pushing, and this will give you the occasion to test, well, to get the results in your own branch.
Wait, so that was remote.
It
Sure.
was
And then
so remote gives you the remotes, and branch
Mhm.
with the verbose options give you the branches and their remotely tracked branches. So it's branch
Yes,
VAE.
also.
Yeah.
But we're pulling this, right? Since that is
Mm-hmm. So you have
oh,
updated. Wait. Yeah. So that would not be a pull. That would be just a fetch. Pull does two things. It fetches and it updates your local branches. But here your local master branch does not track mine.
okay. Oh god.
You have fetched it
Uh,
already, right? It's like this fetch. So it's already done because you just pulled.
mhm.
So now what you want to do is merge that branch here into that. So it's basically git merge and the branch you want to merge in.
Into or the one I want to merge into master.
Yeah, but you're already
Okay.
on master, so you don't need to tell git about that.
Okay.
And that's it.
All right.
And now if you do git push, it will be mirrored onto your own git repository automatically because the one you track is not mine. It's not our brown master. It's origin master.
Yeah. Okay. Okay. um. Right. What we want is to write a character, I guess, or we're starting with the setup, I suppose.
Yes,
Uh,
we can start with the setup. We can start with the interface. I usually start with the copyright.
and you made a copying file for that.
Oh,
Where?
you can open any other like open main and copy it, and that's it. Don't waste time with it. No, not. You know, you can split it into. I don't remember how
Oh
though.
yeah. Uh, tab group or something.
Yeah, that's something like this. Or the plus maybe. Oh yes,
Ah.
that's it. So you can start with the setup, but just one thing.
Mhm.
Um,
Oh.
it's a very good habit to write your interfaces along your implementation. And actually, I write my implementation along with the interface. So usually I write the header file first because you have to balance, um, you have to create a compromise between the implementation, so how you want things to work, and the interface, which is how you want external stuff to use your code. And both go together. You can't ignore either side. You can make it full screen if you want, by the way. Oh, that's nice too.
Uh, let's make a new one. Okay. So you mean you write out the prototypes first and then you add them?
Yes.
Okay.
So when I write the prototype, I'm in the point of view of the user. So I ask myself, what am I going to need? And then I code the implementation, asking myself, so this time I'm in the point of view of the implementation. So I ask myself, what do I need to make it work? You know, and then that's how you see all the needs and requirements of your code emerge.
Yeah, so first you want to initialize it. But we're not sure what we're gonna put in. So it's let's have a look. You want to know the port and you could have the baud rate which is default, I guess, or
We could do that, but again, it's an educational kernel. It's
Mhm.
really fine if we just hard code it in the driver for now.
Okay, just have one COM port, everything just set up.
Yeah,
Okay.
and we'll see what we make optional. Probably nothing. We'll see. Uh, just printing bytes is going to be enough.
Okay. And then once you um, write for output byte,
Oh, write is fine too. We have IO write, so why not?
and that was
Hmm.
um,
So you use a type that is not known by the compiler. Yeah, you have to add the write include immediately.
and also um, is there any other functions we need? I guess for now, this will be okay.
Hmm. You are the interface designer, so I'm just watching, and yeah, okay. It's not stdio, it's stdint.
Oh, whoops. And this is also where we add defines um, some baud and stuff. Have a look at what we need. So we'll add the base address, or I guess it's not necessarily an address because it's an IO port.
It's an address on the port space. So it's a port. That's what a port is. It's an address in a separate space, which is a port space.
Okay.
The IO port space, really. So one other thing. Wait. You have caps lock on. Is that
Nope,
me or you? That's weird.
that was me.
Okay. Um, there is a very strong principle that you should keep in mind, and this is true in any language. You should not make public what you don't want external users to have access to. External users should not access the port directly. They don't need to know about the port. So you should not have that in the
Oh,
header file.
okay.
And that's really what makes software modular and mostly reliable. This encapsulation and separation.
Actually, since well, okay, let's leave it like this. Uh, this. And
You could just write port, it's a little long. Don't use long names if you don't need them.
okay. Tell the connection how fast you want it to be, which is the baud rate, and it has to match with the receiving end. The parity, I guess, you can see here.
Okay, so just so that we don't waste too much time on this, you need to configure the speed and to the baud rate and all those bits. It's done normally with the line control register, if I remember correctly.
Yeah, that's where you set things up.
Where is it? Line protocol, port addresses. Where is it? Really? Is that thing complete?
That's a D lab, right? I think so.
Is this normally? No, sorry, it's this one. The DLab is something else. DLab is a bit. When it's not set, it's basically all registers. When it's set, it's basically those two ones. So you have the same port, see,
Yeah.
which references different internal registers when the DLab bit is set. So yeah, we'll need to set that. But I'm surprised that we don't have the line control register. I'm gonna look for it a little bit because I'm really surprised. But we could use that sequence. Yeah, it's not very complete. But you know what? Follow what they say, and we'll see how it works.
There's also an example, like, or what you've made here. I guess what you're looking for is, would actually be in here. Line control. Wait.
It is. It's here. Yeah. I don't know exactly where, but it's somewhere here. So yes, that's the sequence I use.
Yeah. So you enable the DLab bit, and then you write to it the to the high bit, to the low, or high byte, I guess it is.
Yes.
And then the low byte, and then you clear the LCR bit.
Mm-hmm.
Oh wait. So you could write. Oh wait. Oh, that's weird. It's unsynced now because of VNC. There we
Unsynced?
go. Yeah, my caps was on, and okay.
Oh yes, I'm gonna type it there.
Oh.
The caps lock is on now.
My caps lock is off.
Oh, okay. And now?
Yeah, that works. Okay.
I don't use caps lock, to be honest.
Let's just write it out first, like what we want to do. So we're setting the baud rate. Then we have a look at what our data is going to look like, how many bits, and how many stop bits. And for ASCII, it's just seven bits and one stop bit. I suppose.
Yes, but we're going to use 8 because most serial line software uh, defaults to 8.
Okay. So that is something we'll be writing to the line control register. Up bits, parity. And this is something we're not doing. For now, at least.
No, we're not managing interrupts yet. That will come later.
Okay. Then we need the baud rate. Which at default is value. Are we going to leave this? Are we going to go for this baud rate? Or
Yes.
is it something?
Yeah.
Okay. So then the would you define the devices since it's already? Sure, let's just do it.
No, I would not.
No.
Well, redundancy is a very bad thing. So if you define the divisor from the baud rate, okay, but I don't see why you'd need a macro for that.
Fair point.
Think like someone who reads your code and is going to wonder why you need that macro if it's only used in a single function and is derived from another macro. See?
Mm-hmm.
Do the least confusing thing.
Okay. For this, we need to set the LCR, which we're gonna have some helper functions for, I guess.
Mm-hmm. If you need them, yes. I don't want to, I'm not pointing the way. I'm
Mm-hmm.
waiting to see what you're going to do.
Wait. I'm just gonna go ahead and copy this and
I'd like you
if that's
not to, well, you can copy, of course, but the point is to not copy. If you understand
okay.
what these are and why they have these values, sure, but it's really important that you do,
Okay,
that
then
you
I'll just
that you don't copy blindly because it's really important to understand how things work. You probably don't need all of them either. Only have the one you use, right? To avoid confusion.
an offset of 3. And we're gonna use the um, for now. I believe we're gonna have to use this one eventually as well. But we'll see
Yes,
that later.
probably. But for now,
This
we
is
need the
for
line
waiting.
control register really, and
Mm-hmm.
the DLabs, and the first two ones, the data register, because that's actually where we write. Okay, so let me ask you just one question. Why are you using hexadecimals for these registers? And I'm not implying that you should not. I'm wondering why.
It's just that it's mostly used.
Okay.
From most of the software that I've seen,
Yeah,
it's
yeah. So that's something I want to talk about quickly. Uh, it's something many people do, and yeah, I do it myself even now. I did it a lot in the past. You copy what you see, even if you don't really understand why. Plus, it makes you look like you know what you're doing because hey, hexadecimals. Uh, Avoid that. If there is no reason, if there is no need, avoid it. The only thing you're going to tell a reader who's really experienced is that you don't know why you're doing it.
the-
One good reason to use hexadecimals is when you want to read registers or when you want to quickly identify bits in those registers. That makes sense. But here it's an offset. This is a value that you're going to add. Plus, here in your original data, like the data you use to write a driver, it's not even hexadecimals. So
that's
why?
true.
You,
Yeah,
you see, it
yeah.
doesn't make sense. So I completely understand, and I guess many people in the stream here and elsewhere do that, but keep it simple. If it's not needed, don't do it. That's really a very strong rule that I personally follow.
Okay. We're gonna need the divisor uh, low as well. And the high.
Okay, that's probably fine for now.
Okay. um, okay. And are there any other settings we? So we'll be using 8 bits
Hmm.
and a singular stop bit, I'm
Yes,
assuming.
it's
So that's
called one. Wait, 8 and 1. 8 bits data, no parity, and one stop bit.
no parity, he said.
Hmm. No parity.
Okay.
No parity, no flow control, nothing. The simple, the simplest possible configuration for a serial line. And this is still the most widely used in embedded development because it's so simple. When everything else might not work, usually this works.
This is least two of the significant bits of the line control. Uh, big weightless data.
If you're blocked,
Names are kind
just
of
tell
hard.
me.
Yeah, names are kind of hard, I guess.
Names are hard.
Yeah. Um,
Why that?
data bits, I guess, is what I'm.
Okay.
But
I'd advise not doing that and actually writing LCR because the same way you wrote. So let's take a moment to talk about that kind of naming. I'm gonna take the mouse.
yep.
Um, so can you tell me why you name everything UART like this? here too.
That's to identify the peripheral, I guess you're using.
All right, so
Yeah.
obviously, yes, but why do you use it here, for example, and not at the end or in the middle? Why is it the first?
Because that is, if you would be sorting essentially by name, then that is the first thing you see.
Okay, so it's the most common. It's the one that is
Yep.
shared at the higher level,
Mm.
right? Okay,
Yep.
that is called a namespace. And we don't have namespaces in C. The language doesn't know about them, but we as developers can have namespaces if we discipline ourselves to follow some rules when naming. And this is what we're doing here. Now you have the same kind of thing here. Now you're using register because again it's the most uh, common thing between those ones,
Mm.
right?
Yep.
These are bits in register. So it's not really bits. It's these are offsets. So these are um, internal registers. Okay.
Mm-hmm.
So here you can apply the same reasoning. You have your register and you actually have your bits inside the register. So you make such small internal namespaces to more easily. Well, the first thing is that naming is becoming easier because of that, and then people reading the code will have normally have an easier time understanding it. Because if you write data bits and things like that, so yeah, I understand what you mean here.
Mm-hmm.
Um, you want to separate the value, like the parameter from the actual register value, right?
Yeah.
Okay. Um, so yeah, in this case, that's a good thing to have data bits. But then, personally, what I would do is move them to the top to show, because that's what people read first. So this will show them that those macros are parameters that may be changed, whereas the rest below isn't. And that's it. You can continue.
Okay. Um, but from this name, you can't see that it's 8 bits, which it will be.
No, because it's the value. But then when you actually the reason to have LCR named macros is to name the bits inside the register. But you're not doing
Oh
that
yeah,
right now. You
that's
are
correct.
just
Yeah.
naming a parameter.
Right. And here you use hex.
So no, that's precisely what I don't want you to do. I want you to write 8 because that's the number of bits. And then in the code
Oh, okay.
we can find the value 3 from that.
Right. Okay. Yeah, I got you.
Or let's take a look. Let's take a look. How could we do it? So it is 3. Is it shifted? The two least significant bits of the line control register. Okay, so if you want to write 3, name it LCR 8 bits.
Mm-hmm.
And then it's clear that it's what you write to the LCR register to have this value. And otherwise, yeah, doing it like this would mean that we would need this table, and we'd need to do a lookup in the table to find the bits.
Mm-hmm.
So we could do that, but it's a little tedious.
Mm-hmm.
So yeah, I would go with the LCR bits, 8 bits really.
Like this.
Whatever, doesn't matter. Don't waste time on that.
Okay.
Okay, and here you are using hexadecimal.
Yes.
Okay, why? Again,
Because this is
these
the
are
value.
bits.
Yes,
Okay,
exactly.
so yes, indeed, in that case it makes sense because it's expected that people who have a bit of at least students, who have had classes about binary and hexadecimal should be like not comfortable, but they know that 3 is the first 2 bits. This is something that they should know. And hexadecimals really emphasize the fact that you're interested in the bits or the representation, not really the value itself.
One stop bit, no parity. That's also in LCR, the control register. That bit 2.
Mm-hmm.
0, 1, 2. Okay, yep.
You can just
But
call it stop.
setting, yeah, but you're setting it to a 0 though. Would you be clearing it then? I guess.
I'm not following. Or
Yeah,
is it 0?
it is 0, I
Oh, it is
believe.
0. Oh, okay.
Yeah.
Okay.
So the default is
I see.
set to 0.
Yeah.
And this one as well.
But it would be stop 1 then.
Oh, yeah,
The
of
name.
course. Mm. Gonna be long.
None, but you're not telling what it is. So it should be, yeah, parity none, for example.
That's also 0.
Oh, really? Okay.
But then you need um, you I probably clear this then. Just get the how many bits is it? 5 in the control register?
Uh, you want to clear them?
Well, is it so that they are initially 0? Is that something you can depend on?
Um, why? So why are you asking? What are you intending to do that would rely on that?
Well, I mean, there's the registers, the initial register values of LCR,
Okay. But then how
and
are you
I
going to
don't
use that?
the default values. You mean, or
Now I'm asking, why does it matter that previous values have, like, how could I say that? Why do you care about what the register is? You're going to write it. So I assume that you're asking because you want to not write it completely.
yeah, sorry, yeah.
And how could you do that?
Um, you toggling bits, I guess, is something you don't have to set the entire register,
Okay, so
but that
let's come back to. Wait, I'm lost. Um, oh, wait, no. Very bad with the mouse. How do we open? Oh, okay. Other documents. Where is IO? Oh, okay. It's not everything. It's just the recent ones. You're writing entire bytes here.
oh right, yeah,
Yeah, that should answer your question right away.
yeah, okay.
So just to go up to follow up a bit on that, um, it's not always the case that you erase all registers. So it's a very good question. In this case, what you do is that you read, modify, write. So you read the register, you clear or set some bits, and then you write. And in this case, yes, it might be important to have a good specification about the default values that you expect. Yeah, that's a problem I've had on ARM recently.
Okay.
So
Yeah.
it does happen, and at work too, and in general, really, it's quite common. But here, it's entire bytes, so yeah, you don't really care, and you don't have anything that you want to keep. You can apparently you have to set everything anyway. So
Mm-hmm. Yep. Okay. Uh, so let's see how we write to it. Set the most significant bit in the LCR, and then you set the divisor, and then you clear it again. That's for
okay,
setting the baud rate.
so I would advise you to not, like what you just have here, comments, is something I consider bad habits. So it's personal,
Mm-hmm.
right? But I still think I'm right about this. Like I insist on it. That instead of having comments, uh, change the code so that it says what the comments here say.
Oh,
So
definitely. Yes. Yeah.
so
It's just so I
just
don't
have a
have to
function that
switch.
set that sets the baud rate instead. And inside that function,
Oh yeah.
you can directly write the code you need.
The comments were more for me, so I don't
Yeah,
have to switch all the time.
I figured.
Uh,
But remember, it's educational. People are watching.
that is true.
You might give other people bad habits without knowing.
And these would be static.
Yes, so careful about that because in C, um, you have to remember that the language works with forward declarations all the time. So a symbol cannot be used before it has been declared. No, 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 wait,
Oh
wait.
wait.
Careful. That header file is your public interface.
Yep.
You do not want to change it unless you want to give a new service to users.
And this is something that's not important to the user.
And I would say that the user must not have access to that. That's encapsulation here. You just want to write it before. Yeah. Now here, you're making a prototype, but I would advise against that because, I'm taking the mouse, because that leads to duplication. You don't need duplication. You can grab
Oh
the whole
right, and just
function,
write it above.
you can put it here and it will work. And you have defined it a single time.
That's true. Yep. But then you'd have to be very cautious of which uh, functions you use it when. Uh, yeah, what other functions, I guess,
Um,
or would
sure,
you have
but
the?
it's a single file, so it's a single functional unit. So you're supposed to, yeah, uh, it's supposed to be coherent.
Fair enough. Okay. So we need. What's the I/O? Open that in here. Um, so we were writing to the COM port plus the LCR
Mm-hmm.
to get the offset. And the byte we'll be writing is the.
Yeah, you need to
Actually,
define it.
that's. Yeah, this, essentially. Because you need.
Mm-hmm.
I believe it was the most significant byte
Yeah,
or
that's it.
bit.
It's an
What you're
LCR
doing
bit.
is it's an LCR bit of, well, it's the LCR MSB essentially. But
Yes,
what
but
it
wait.
doesn't tell you, it's a
Yes, it
DLAB.
has this name. It's called the DLAB bit, like literally the DLAB bit. So you can just call it DLAB, and it's an LCR bit. That's what I'm saying.
Ah, fair enough. Okay. Yep. Bit, I guess. Doesn't
You
really
don't really
matter.
need it. Makes
There
like
we
if
go.
you don't need it. Now, if you have it, it's not bad either. Just don't waste too much time on that kind of problem, and don't look for extreme coherence. Like if sometimes you put it and sometimes you don't, it's fine. You don't have to change everything you did just so that everything looks the same. It's I've seen people with that kind of uh, almost OCD behavior in coding.
Yeah, and then it takes a little while.
Yeah,
uh,
it makes them very not productive, and they know it.
let's have a look. The divisor. It will just be dividing by 1 because we're using a uh, default
Default.
value. I believe the default was 115.
Oh no, it's not the default. It's that the internal. Wait, I'm taking the. Oh, okay, the user won't use this. The reason is this: the internal clock runs
Oh,
at this speed.
right. Okay.
So a divisor here, or divisor, I'm not sure how you pronounce it, divides the clock. So basically, it skips some ticks. That's how it's programmed. It's basically a counter. Every n ticks
Hmm.
you let it pass, the others are masked.
Yep. Yep. That makes sense. So here, uh, that would be no. Um,
Wait, one thing
oh,
though, one
whoops.
thing important.
Hmm.
Um, Here, you write the entire register content as being only this bit. That's probably not what you want. Well, in this case,
I'm
maybe
not sure.
actually.
I'm not sure.
Yeah, maybe that's what you want. The first time, yes, but then you'll want to keep the previous value and not erase what you have written before. See what I mean?
Not entirely. No.
Okay. Um, so
Okay.
the LCR register here, this is a single register, okay, of 8 bits. Here, what you write is this entire value. So basically, you write the DLAT bit to 1 and everything else to 0. So you erase what was before. It's okay now, but later, when you want to reset, when you want to clear the DLAT bit, you will have to keep what you have written in the LCR register, right? See
Yeah.
what I mean? Like, or maybe, yeah, maybe what you could do is when you clear the most significant bit, you can also write the rest at the same time. You can do that too. I'm going to shut up now. Sorry.
Uh, Still not entirely sure. So okay? So you have the MSB. This basically allows you to access the control register.
Hmm.
After that, you want to set it up,
Yes.
and we'll be giving. Well, this is actually for the divisor. It doesn't yet know.
So what is the problem?
I'm not quite sure what you meant. For this, I don't think it's very important to know what we um,
No, the first time is
keep.
not. I see what you mean. Okay.
Yeah,
Just
this is
ignore
just for
what I
setting the
said.
bod.
Ignore what
Okay,
I
okay.
said. Just go ahead with what you had in mind first, and that's why I said I'm sorry. I'm going to shut up because you're good on you're on the right track.
Um, You'd be using the baud rate, I guess.
Mm-hmm.
Um,
But the baud rate, you see the value,
it's
it doesn't
1.
fit in 8 bits.
But this is not something we're sending anyway, because this is the clock that it runs on.
Oh, this is the
Um,
value that we want too. So you could
okay.
have you. Uh, 1 second. Whoops. Okay. Um, let me take a look because I don't remember exactly how it goes. So the divisor value. Okay, so the divisor value here was chosen to be 1, but
Mm-hmm.
here is one way you can have it. You could say so UART. We could call it clock. Is this value. Now this is not an argument, so we move it below. And then you could compute the divisor this way.
Ah, right. Oh, that makes a lot of sense.
And if you want to make like the speed and other things optional through additional functions in your public interface, now you know how to change the speed. It will be this
Yeah,
algorithm,
but
so simple division, but instead of being a macro, it will be coded. Like there will be actual instructions for it and a
uh,
function to pass the value.
but the divisor is always a. Uh, this will be an int, obviously. So if I enter this, it's still going to be 1. Like it doesn't actually scale to this
Yes,
speed.
it's an integer division,
Yeah, yeah,
so it can't be any value.
yeah. And
By the way, you are using IOWrite functions, but the compiler doesn't know about it.
oh,
I'm just anticipating the warning and link error
exactly. Yeah.
as a human compiler, but yeah. Okay. And being a complete freak about coding style,
Mm-hmm.
I usually sort the headers alphabetically because when you start to have many, it becomes easier to find them.
Fair enough. This this is going to be 0 for our case, but
Hmm. So how you come up with 0 from that? That's the question, right?
shifted to the left, I suppose.
The right.
Oh, right. Yeah, yeah. Because you're shifting the most significant bits to the right
Hmm.
side, so you can. Yeah, gotcha. Um,
Okay, wait.
mhm.
What does this do?
And I'm not sure it's gonna work. It's the inverted of DLab,
It's a complement. So
which
yeah,
is
all bits
7F.
are inverted, but that's not really the word. The word is complement. So what is it going to be? What's the value that you're writing here?
7f.
No.
Then.
Wait, yeah, sorry, 7f, yes.
And what you want to do is you want to clear it.
You want to clear it, but you don't want to change the rest, or maybe you don't care about the rest because you're about to set it after. So I'm gonna step in for a bit. Um, you have a couple of ways to do that. Either you assume that there will be a fixed order of setup. So, for example, you're going to set the baud rate first, and then the parity, and then the stop bits. And in this case, you can just assume that you don't care about the previous value of the register, or you decide to be as generic as possible, and you assume that the register might have valid values that you have to preserve. In which case, you have to read it, and then write, like, modify the bits you're interested in, and then write the result, which would require me to write an IO read function, by the way, and we'll probably have to do that. We'll see, maybe not.
Okay.
Actually, here, what's happening is that you can configure the stop bit and the parity and clear the DLAB bit in a single write. So that's probably what we're going to do. Now, the problem with that approach is that this name here is not valid anymore since we are configuring more than the baud rate. And because we're doing all this in a single step, we're going to do it here. Set this value by writing. Okay, this is done. We don't need the comment anymore. Okay, you can just take that function, put it here, remove it here. See, no prototype to remove. Simple. And then here you have to write, so you don't have the DLAB bit anymore, you have other bits. And it's now yours.
But these are going to be 0 anyway. Which then still...
Not all of them.
This one at
and
least,
even if they are 0, you may want to write them so that people read the name of the macros, so that they actually see that that's your intention. You make it explicit.
It'd be too long.
I'm not sure why you removed it.
Well, it's going to extend past the thing.
Oh, don't worry about that. You can align it, or you can use a temporary variable. It doesn't matter. But if you align it, yes, like this, perfect. Okay, is anything else needed actually?
Advisor. Let's stop at periods. Don't think so.
It looks good to me. We can probably start writing bytes now.
Okay. We'd still have to clear this.
No. No, we don't. Look, your last write does not include the DLAB bit.
Oh, so yeah. Okay. Yep. Now I get it.
It's not a read modify write here. It's just a write. You erase everything. You set the values of all bits. So here it's clear. Someone reading the code will see 8 bits, top 1, parity none. And unless the values are wrong, which he can easily check by reading the macros at the top of the file, it's going to be obvious. Doesn't need a comment, and it will work. It should just work.
Okay. And writing to we uh, need the data register, which hasn't got an offset. But I guess
Yeah,
for
it's that one.
clarity, would you use this for clarity, or would you just
Oh yes, I would definitely.
okay? Um, and then it needs the dlab bit set to 0. So this is just where we.
It's already set to 0, so yeah, you don't need anything else.
That's it.
You're good. And that should be it, normally.
Yep.
Okay, so I guess it's fine. You can commit that. Well, test it a little, at least test it before committing. So you've added a new file. Um, you've added with Git. That's good. You need to add it to the make file as well.
Uh,
Okay. No, don't commit yet. Test it. Make sure that it builds. Make sure that it runs. Stupid me. That's my mistake. I didn't test. See? So yeah, we're gonna do something ugly. We're gonna fix that in your commit. It's not clean, but it will be okay.
okay. Oh. Um, there we go. And we don't really do anything with this yet.
We need to test it. We need to do something. At least initialize it.
Keep that for now. Oh. Is that in here? Yeah.
Think about the headers. When you use a function,
Good
ask
point.
yourself where does it come from? How does the compiler know it? In C, characters have single quotes. Yes.
Yeah, it
Oh,
works.
first attempt. Very good.
Awesome. What was the command again? It was Control A C. Okay, yeah, just to test it.
Mm-hmm.
Cool. And then we git commit dash A.
Mm-hmm. Exactly.
And what do we do? Do you want to add the well, the defines bit is just a little error, I guess.
Add everything because we don't really care about the history. It's likely that at the end I will erase the history anyway.
Okay. Uh,
Okay, so small talk on this. You have two schools about commit log messages. Um, one which seems natural because now that I remember, I used to do that too. Is to use the past form. added. See,
Yeah,
did this, did that.
added.
Um,
Yeah.
and there is another way, which is, I don't know, it became more natural to me with time, and it's actually the major style used in big projects like Linux, is to use the, I don't know the word in English actually, but yeah, a present form. Basically, it describes what the change does because it's not considered in the past. The change might be, like the commit itself might be cherry picked and used on other branches. So there is no notion of time. It just mentions what the patch does. And the patch adds a UART driver. So add, yeah, whatever you want. Device driver, whatever, I don't care. But
Yeah.
it's basically the tools calls. None is better, I don't think. I personally use this one now. Also, it makes your logs slightly shorter.
That is true. Yes.
If
So
that's an argument.
yeah, yeah. Reading less is always good. These kind of things.
It
Okay.
matters if you want your code to remain um, slim, I guess, like
Mhm.
so that the code does not exceed the 80 character limit.
Yeah. Uh, so this is just git push, and then I'll do a pull request, I guess,
Okay,
which I'll do on my machine.
okay, sure. Now, I expected that this would be done pretty quickly, and as you can see, it's really easy. I'm not sure this would really work on real hardware because real hardware can be picky. There's a good chance it does. I don't know. We have to test. For now, it doesn't really matter. Um, so the last part of the stream tonight is going to turn this little driver into something that is used by a printf implementation, so that we can actually have complex formats. Um, there was someone last time, I think it was Tuesday, who was joking about, oh no, printf is too complicated. Let's write a driver. Look at this driver. It's 50 lines of code, and most of them are, no, it's not even 50, like half of it is the license. A third is macros, and the code is just a couple of lines. Drivers can be very simple. Printf, imagine what printf has to do, all the formats it has to manage, with all the requirements, the modifiers, the specifiers, etc., etc. It's vastly more complicated. So we're not going to implement printf. We're going to port it from somewhere. And we still have to agree on that because as an educational project, it makes sense to show people that things can be reused, but at the same time, we don't want to reuse everything so that nothing is done. So for now, the limit I have in mind is my small repository of basic C modules, which implements like linked lists, trees, so printf and scanf2, and other things like that, like a circular buffer, hash functions, that kind of things, which are part of the, the basic development toolkit that you will find in most languages, except C doesn't have one. The C library is extremely crude and simple, and uh, and so instead of implementing those basic tools and services that are expected in almost every language, um, we don't have time to write them. It's not interesting. We're going to reuse some code. Now, that code is going to come from this. So, C.NET Basic Modules Library for C. This is the modules we have. And in this, we have the format module. which gives printf and scanf. It's a subset. It's not a complete implementation. We are probably going to use the list module too, and maybe the shell module at the end. But before we can use the shell module, we are going to implement interrupts, and we're not there yet. Okay, is the pull request done?
Yes. Yeah.
Yeah, you need to tell me, because
Sorry.
otherwise I don't know. So pull requests. Okay. Merge. Confirm. No comment. Oh, okay. So is it done?
Yeah. Yeah.
Okay.
Same thing as last time. Yeah, GitHub isn't that clear.
Yeah, I never use GitHub, so.
No.
C8. C8 is a bit late. Yeah, you have to watch because it's the most, like, you just missed the really interesting part of the stream, unfortunately. Um, but we're still working a bit, like maybe half an hour, 45 minutes. Okay, so I'm going back to my screen, fetching the changes. Oh yes, I have two repositories too, that's right. So fetch from GitHub. Okay. And now merge GitHub master. Okay. So my branch is up to date. I'm going to update my own repository. So it's very similar to what you're doing on your side for almost the same reasons. Okay, we have a new UART driver. That's great. Going to make sure that it also works here. Yeah, it does. Okay. Now, actually, before committing, we should have removed the test here, but that's not important. We don't really care about that. Okay. So let's actually have printf. We need two things to have printf. We need the format module, which I'm going to import. So yeah, it helps that that you have MIT code, MIT licensed code, because then you can reuse it almost everywhere. See, I just have to copy the files basically, and I can use them legally without any problem. And actually, like, it's not really important for the project we're doing now, but imagine yourself at work and you're on a project that has no linked list. Are you going to implement a new linked list once again? That makes no sense.
It's no.
So having that kind of open source code that you can really reuse everywhere is really valuable. So think of it if you have that kind of need. I'm going to add that to the makefile, and I'm going to reorder the way we list our sources, like this.
Having those kind of tools is actually exactly what I was looking for quite recently with the circular buffer.
Oh, yes, right. So did you actually use it?
I haven't worked on it further since then,
Okay.
but I will probably use that.
All right. So now I don't see it built for some reason. Oh, because I didn't add it. And let's reorder that alphabetically. Okay. Oh yes, we do not have assertions. That's right. And the compiler doesn't provide them. That is right. So we could just reuse assertions. So yeah. Right, it doesn't provide assert. Let's take a look at assert. So this is the assert header. It is standard in both C and POSIX. I think. They don't say it here. That's weird. They define the assert macro, and assert is defined as a macro. It's really like it has to be a macro that only exists if the macro and debug is not defined. So we could have assert. Assert is really useful. Okay, let's have it quickly. Let's take a look. So this one, yeah, this one won't do. The license is not what we want. And since I have written the code, I can relicense it. Normally, I should keep the license bits, but I mean, it's 20 lines. Who cares? Oh, this is C11. We're not doing C11. Macros, panic, no. Although we're going to have. How are we going to call it? We could call it printf or stdio. I don't want to call it stdio because it's really standard, and we might not want to like if a student comes here, reads at that, and sees stdio, it may not like it may be confusing for him um, because it's a standard header. So he's going to wonder, for example, how a standard header, which is in USR include, gets used in the kernel. So I'm going to use another name, printf probably. Okay. Oh, we need macros, definitely, definitely. I should not have removed that. Let's import them too. Hmm. Okay, so let's take a look at this file, macros. Again, I have to, well, actually, no, the licenses is correct. This one is really specific to the GCC compiler, and not all of it is really useful, but some of it is really essential. Array size is essential. In my opinion, you cannot, well, you can, but it's very difficult to write good code in C without that macro. Because it means that every time you have a static array, you're going to use like the macro used to define the size of the array, or you're going to use something else like an integer storing a size. In any case, it's not optimal. Um, some arrays, for example, are declared using some size, and sometimes you have plus a value because you want to account for some data at the end. It's common for the strings, for example, where you need to store the null terminating byte character. Um, Array size makes it certain that you do have the size of your array, even if that changes, even if you change everything else, anything else really in the code, the size of your array will be right. This macro should be standard C. The quotes macro are useful. That's what we're going to use here. Those ones are convenience to write multi-line macros, like function-like macros. For example, those ones are standard. This is an integer division which always returns the ceiling, not the floor, so it doesn't truncate. This is power of two alignment. This one is quite useful. It uses offset off, which is standard and provided by stddef. And basically it allows you to obtain the parent structure of a member, provided you have the address of the member. So basically, you know the offset from the beginning of the structure to the member. So from the address of the member, you can find the address of the parent structure, and this is really convenient. Likely and likely are optimizations. Um, we don't care about them. It's really micro optimization. Buyer here is really important. Um, Buyer will make sure that when we do need it, the compiler will be forbidden to reorder code across the buyers. And in order to implement critical sections, we need something like this. Hello Medusic, correct me, but it will silently return garbage if your array ever becomes pointer in the process. Yes. Yes, it will. So it's
Okay.
really meant for static arrays. It's not perfect either. I agree with that.
The array size, you mean?
Yeah.
Yeah, okay.
Um, these are convenience, not really useful. Let's take a look. So yeah, the file was made for C11, so some of them, like alignment macros, have um, have been removed. But yeah, what you should remember is array size, struct off, and buyer. These are really the three important ones that should be standard. Okay, so let's add the macros first. So printf, yes, we don't have printf. Yeah, let's write it right away. So I'm going to use your file as a template. Let's take a look at the interface. So we want something standard, but we don't care about it being too standard because it's our kernel, it's our environment, it's our rules, we do what we like. But standard means that people who are working with it know what to expect without rechecking again. In game dev now, I want to work for Sweden's Secret Service as a tech guy. I think you understand. Would studying computer software engineering be good for that? Sure. Yeah. You learn a lot of things through low-level system development. And yeah, about security as well. Okay, so we want something that returns an int. Okay. Printf, then we have this. Okay, format, and then we have variable arguments. Okay, so that's basically our function. One thing we could do, I won't be doing it here, or maybe I will, I don't know. It's quite convenient. Let me show you. I think it's here. Yeah, it's the format attribute of GCC, which basically tells the compiler that your function is like printf, so it accepts the same kind of arguments, and so the compiler will perform the same kind of checks. So if you use an invalid format or you don't have the right number of arguments, the compiler will tell you, and it's convenient. It catches a lot of mistakes. So we might want to do that. Let's actually do it. Now I'm not going to write vprintf. Um, it could be a nice thing to show a case for variable arguments, but it's not really. I don't think it's essential. So until we really need vprintf, I will not implement it. We don't need stdint. We don't need anything really here. Okay.
We'll need the define.
Yes.
If not define,
The
define.
inclusion guards, yes.
Inclusion guard. There you go.
And in your file too, by the way, we forgot that.
In the UART one?
In yours, I think, no?
I'm asking the UART one.
Yeah,
Oh yeah,
UART
yeah,
one.
we
forgot that.
Yep.
So yeah, I'll add it to. It's not going to be the cleanest history,
Yeah.
but
Fine.
it will do.
I've also noticed that in the UART, yeah, to the left you can see the void is actually in just in front of the function name, whereas you leave a new
Yeah,
line.
that's okay. It's not my coding style, but I don't expect. Well, I will probably turn it into my coding style at some point. But again, it's like the Git history. It doesn't really matter.
Yeah. Yeah.
Okay, so actually, yeah, we will have a standard, an stdarg use case with printf alone. So printf, how do we write printf? Do you want to write printf, by the way? What we could do is that I give you the tools, and then you write the implementation. But for that, you would need to use that stdarg. Do you know stdarg?
I've used it a little bit, but I'm not very familiar with it.
Do you want to try?
Sure.
Okay. So I'm going to write that first. Okay. This is your function. It's going to return something. This is what you can use, basically. You probably want this one or this one. Yeah, this one probably. This one is the one you want to use. That's it.
Okay. I'm not sure if I then have enough information.
Because if you want to do it, it won't be on my console. So it's 30 past 10. So it's
why don't you go ahead and do it?
Hmm?
Yeah. Why don't you go ahead and do it then? It's
I mean, I was about to say it's kind of early for me. But yeah, maybe people want to see it, to watch the stream until the end. So let's make the stream a little shorter. I'm going to do that. Okay. So this here is basically the stack. And we're going to need accessors to the stack. We don't know that it is the stack. It may not be the stack. It depends on the implementation, but it's almost always the stack. What we want is, so stdarg-h, we want to use these things here. Okay, I can close that for now and code it with the man page nearby. The first thing I want to do is have a buffer. Now, that buffer is going to be limited. We're going to explicitly mention in the header that calling printf with strings that are too long will not work. They will be truncated. I'm not implementing it like on a Unix system with a stream, an output stream behind. That would require more abstraction. That's not the point of the project. So we make a simple buffer. We produce the output in that buffer, and then we write the buffer to the UART console. Very simple. Now, what size and where is the buffer? The buffer could be here on the stack of the function, but then it means that it cannot be too large, because if it's large, it could overflow the stack. Remember, we are running with the stack set here. Which is only 4K. So if you create a buffer of, say, well, 4K, for example, you're going to extend beyond the stack and you might erase data that you shouldn't. You tell me, Metastate, if something is right. Hello?
Yeah, hello,
Okay.
yeah.
I was wondering if I was disconnected. If something is wrong, if you don't understand, if you want more details, please intervene immediately.
Okay.
Okay, so we want to save the stack and save ourselves from mistakes. So I'm going to create a buffer here with a size. Let's say we want, I don't know, 1K. Okay. So another precision. Um, the kernel is currently not multi-threaded. So we don't have problems like reentrancy and thread safety. But at some point we will.
How would that mess with the buffer? Just
Well, if you have several threads calling printf at the same time, using the
oh yeah,
same buffer, and
yeah,
you don't
okay.
do anything else, you're gonna get garbage. Or worse, it could corrupt your memory elsewhere. Okay, so now I'm going back to the format header, which I'm going to use. Okay. And I'm going to use this variant for multiple reasons. First, there is the v. The v means that it takes a va list argument, because you can't pass that kind of argument, which is really an argument list. You can't pass it directly. You need to pack it in some object, which is exactly what va list is for here. The second reason is the n. The n means that you have a maximum size, which will allow me not to overflow the printf buffer. So let's create the va list first. We need va start, right? Let's take a look. Description is invoked to initialize AP to the beginning of the list before any calls to va arg. Okay, and then we'll need va end probably. Okay, so va start. We need a va list. And here the argument, so it's probably better here. Okay. The argument last is the name of the last argument before the variable argument list. So that's basically format. Immediately va end, not to forget. Okay, does I have an example? I have one with copy. That's not exactly what I'm looking for. Ah, great. Okay, so that's basically what we're doing. Exactly. Now we don't use va arg because instead we are passing ap to vsn printf format. Sorry. Okay. So the string here is the buffer that we want to fill. So that's printf buffer. The size, well, it's its size. I don't want to know the size. I certainly don't want to reuse that thing here. Absolutely not. I want to use size of as much as I can, because that's really the size of what I'm using, and there can't be any mistake here. Then we're going to have the format. Well, it's that thing here, and then the va list, which is ap. Okay. Now our function returns a length, and actually what is returned by the printf, or like all the printf functions, here is the same. We don't really need to know what it is, but for our curiosity, it's the number of characters actually printed excluding the null byte. So int length, we could call it ret, why not? That's it. And I mean, really, for the most part, that's it. It's not complete yet. We have generated the buffer, but we need to print it. Hello, Roberto. T'as vu avec l'accent et tout? Okay. Now, in order to print the buffer,
just to be sure, the buffer size of printf actually reserves some space within the stack that you have already.
no.
Or is it a new stack that you
This
add?
this is not on the stack. This is static storage. So it's going to be in the data segment. Remember the linker script?
Oh yeah.
It's going to be here or
Okay.
here. Actually, since it's not initialized, it's going to end up here.
Okay.
Okay. Here is my iterator. We actually need the length. We need to know what it is. Now, one thing is important here, though, about the length. We don't want... Wait. I think the length, in this case, is... yeah, do not write more than size bytes. If the output was truncated due to this limit, then the return value is the number of characters which would have been written. So it's not length that I want to use. And yeah, be very careful about that kind of detail. That's why you have bugs in code. Those details are the cause of many, many bugs. So instead, what I'm going to do is that I'm going to rely on the fact that the null byte is always written. Is that mentioned somewhere? The functions write at most size bytes, including the terminating null byte. So there is always a null byte. Are you implementing a printf from scratch? No, I'm reusing my own implementation in the educational kernel. But I am implementing printf from scratch. Like this small code is from scratch, but this one, which is actually vsn printf, it's a different function, is not. So how could we do that? Let's use a pointer. And actually, let's make it an iterator. Like this. And now I'm going to print to the serial device. So what's the interface? It's only the byte. Okay. Now I have a small problem, which is that here I have chars and here I have unsigned ints, integers of 8 bits. Basically, I'm sending signed to unsigned. It's not really a problem. I'm just going to force the cast so that the compiler is happy. I know that the compiler will not change the internal representation, which is what I'm actually interested in. So this is fine.
Internal representation? How do you mean?
I mean that if like the actual bits in the integer will remain the same. The compiler is not going to change them when casting.
Okay.
It's completely passive. I'm not hearing you very well right now.
Oh, sorry. Yeah. No, I had my hands
Okay,
in front
I
of the
see.
microphone.
So printf buffer. No. pointer, actually. Like this. Okay. And return length. Alright. Does that work? Limits. That's probably my own file. Yes. I hope it's not C11. So it does use limits, and limits is normally provided. We're not going to include it. String. Oh. Oh, yeah, we need basic functions, that's right. We're going to need string functions too. It's actually easy to write, so let's see. What else do we need? stdio, okay. String. This one is probably something we want to actually implement. So let's do this right now. I'm going to copy defs into string h. Errors. Right. Not going to implement that either. I'm going to just copy the definitions from the source, like I did with chart bit. So this would be, let's see. Okay. We have no resolution again. Format. Okay, only 3 of them. Actually, we could use no. Wait, no, we're in the kernel, we can't. Light to yellow. What if your char type would be type deft to unsigned char? This cast would break the code, wouldn't it? How? Is it solved in that actual kernel that is cross-compiled into platforms like ARM, which type deft char to unsigned char? So it really depends. Here is what I do on my kernel. I use this option. So in my own kernel, char is always signed. Now, I don't understand why you say that it would break the code if char was unsigned. And just to be clear, in the C specification, char is its own type. It's not an alias for signed or unsigned char. There are 3 char types. And char can be either unsigned or signed, and you don't know. But I don't know, yeah, I don't know why you say it breaks. I'm curious. Okay, now we need EOF.
Actually, a good to do. I said that's actually a good to do because that has messed me up a couple times.
Yes. What a strange design choice. To make char unsigned? No, not. Oh, you mean that CS3 types? Yes. I want 10% of your skill level. It's really not that difficult. It's well, it's a lot of practice and time, really, and and listening to advice, I guess, and judging them. That's probably the most tricky part of it all. Okay, size T, that's not known too. Okay. So we have two functions to implement. And in my printf, I made a mistake here. The cast is wrong. Yes, I forgot the pointer. Okay, so now we need that because my format code actually handles long, which is a 64-bit integer format, and we are on a 32-bit processor, which does not implement 64-bit operations. So we are going to need help to implement that. And then we'll have to implement those string functions, which is going to be very quick. I'm just going to copy the code because I'm not interested in that. Again, it's part of the toolkit that everyone should have. Like it's in the C library. So I'm just gonna grab code that I know works, and I'll be fine with that. Now, no previous prototype for printf, really, because yes, we did not include its own header. Okay, so now we have no warnings, which is great. Are we actually building the format file? I don't see it here. It's here though. And oh, I must have left the info directive. Yes, okay. But format doesn't seem to be, oh, format S, yes, all right. Okay, that's better. So implicit declarations, okay, let's code that quickly. So copy string H to string C. Let's add it. And immediately, oh yeah, let's add it to the makefile too. Oh, we do have it already, my bad. Yeah, it's not a header file, we can remove that. And let's just grab some code from here. So we need strcopy and strlen. Okay. Those implementations are really simple. Like, I think students shouldn't have problem with them. It's just too simple. Whoops. Okay. Do we need to include anything? We don't have not pointers, we don't have special types, but we have size t. So we do need stddef. What else? That's all, I guess. Yeah, I forgot to export them into the header, and the compiler is probably using built-in definitions. Undefined reference to strcopy, that's the right one. So something is wrong. Not sure I see what it is. It's probably the make file. Yeah, string is not here, that's why. Okay, So now we only have to deal with that. And I'm going to take care of this right after I read the chat. Dumb web developer here. Ah, being a web developer doesn't necessarily mean you're dumb, you know. You have a chance, sometimes an opportunity to do complicated stuff too. But even as a complete noob in programming, I can feel Synox is very good. Too many people rely on impressions. As an anecdote, one of our interns told me like something like this one day, and I asked him, "How do you know?" And he told me, "Oh, because everyone says it." But he never read any code. He didn't actually know. He just gossip, and it may just not be true. Like it's like this prophet in the Matrix Reloaded who says that you do not know someone until you fight them. Like it's the same with code. You have to read their code and then you know them. Oh, actually it's in printf, so the bits will always be interpreted as characters and not as some numbers, so never mind, sorry. Yes, that's it. Now, with this problem, so there are solutions. Usually the solution is to add a library, which is specifically meant to implement those functions. Those functions are part of the ABI, by the way. So their name, their interface is standard. If it's not standard, you usually have choices. For example, on ARM, VFP, for example, let's take a look. Or maybe I can just take a look at the compiler documentation. We have that. Yes, okay, so here, for example, this is the FPU argument for the ARM architecture. Now, unlike x86, ARM has many different implementations of floating point units, and actually that's also true with x86, except that they are like it's the SSE sets of instructions. So it's comparable, but it's more complicated on the ARM because on x86 the coprocessor has been standard since the 486. So the 486 was basically 30 years ago. Whereas on ARM, it's common to see processors that do not have a floating point unit for cost reasons, for example. And because of that, you have many legacy interfaces, and so usually you will have hardware. But if you don't have hardware, you will have call to libraries, and um, some of these interfaces really, or hardware emulation. See, this is what they are. They emulate the hardware. So they implement operations like divisions, 64-bit divisions, floating point divisions, multiplications, usually it's that, um, in software. So it's very slow. If you care about performance, beware. I've known projects where people do a lot of double calculation and they do not have a floating point unit on their processor, which means that it's all software practically. And they only realize that after they had the hardware. So um, here we are going to use a library, but fortunately the library comes with the compiler. It's the libgcc library. And so I'm going to copy that too because it's tricky.
An alternative to floating points would be fixed points, but
What?
I said an alternative to floating points. If you don't have an FPU, then you could
Yes, but
decide to go for fixed points, but you lose a lot of.
it's rarely used. Floating point is much better, even in software. So you can't do real math with fixed point.
Okay.
Well, you can't really do real math with floating point either, but it's much more precise. It's much closer.
Yeah, lose a lot of
Um,
precision.
we have problems with matrix inversions, basically, because some values can be very close to zero and be interpreted as zero, despite having doubles. With fixed point, which was actually attempted at the beginning, it was just not working. We would have
Okay.
errors all the time because of the lack of precision. So here it's in the LD flags. I simply add this. So I link the libgcc library as I would any regular library, except that libgcc can be used in kernel mode, whereas most libraries are expected to be used in a hosted environment. Okay, so much better, except the string file doesn't include its own header. Okay, everything is good. Yeah, I haven't actually used it. Really? There you go. Hey, how about that?
Awesome.
Okay, let me look at chat quickly. Well, I said I'm a noob. I realize it. Sadly, I can't even count on any skill in programming, so I'm left with intuition. Yeah, I understand what you mean. But you can, I mean, when you read code, you can somehow, even if you're not good at it, you can somehow feel whether it seems better than other code or not. Usually, like if it has 5 to 10 indentation levels, usually it's not that good compared to one that has like 2 or 3. It's like it looks good, even if you don't understand details. It just looks good. Now there can be code that looks good and is crap too. That's also a thing. By the way, tomorrow my university hosts an RT summit. Let me take a look at that. Real time with the Linux Foundation. Oh, well, lucky you.
That sounds really cool.
Will you have desktop environment? Well, maybe, but it's the least priority, to be honest. If so, how do you plan making video drivers, or you can use something? So drivers in general, including video drivers, are going to be reused, probably from Linux in user space. So there will be something like a DRM server and memory mapping through the microkernel of the memory, the GPU memory. The only overhead will be messaging to implement system calls. And normally, like ideally, the user space environment will be very um, like it's going to be almost only glue code in order to import drivers from other operating systems. Well, kernel has nothing to do with desktop environment, and I'm talking shit here. No, it has a lot to do. I understand what you mean. You can see the optimization, I guess, at much basic level. There is already that. I'm not talking about the optimization. I'm really talking about code that makes sense versus code that doesn't. Oh, she has. I don't see that, but I'm on my laptop. It's an 11 inch, so I don't see much. Okay, so we have something that works. We have output. That's great. Um, we have assert, and assert uses printf. So let's make an assertion that fails, just to see that the chain is decently implemented. Oh well. Undefined reference. Okay, I need a cert. Okay. Yes, that's right. That's right. So it has to include macros. Okay. Okay, and now we have an assertion failing, as expected. Except that it was the panic function, and the panic function adds a new line at the end, which we don't. But basically, yeah, we have a printf, and a printf that should support quite powerful formats like LLU, for example. Let's add a hash pound. Let's make it, I don't know, 20. Is that a thing? I'm sure it's a thing. It's probably this way, yeah. And with zeros. And I'm going to write 1, 2, 3 in hexadecimal. Oh, see? See the warnings? Expect. Oh yes, that's right. Um, that's what printf is able to do, and that requires some code. So now that we have a very good printf, we're going to be it's going to be very convenient for us to code. We won't have to look at registers and assembly all the time. We can go, we have an additional layer of abstraction, we have text, we have messages. So that's a great thing, really.
That helps.
And only after 2 sessions, well, we copied some code, but the point is not to start from scratch and do everything by ourselves. So that's something you should be able to do in other projects too, reuse code and go fast.
Exactly. You'll be Googling for stuff and then you'll use that as well. Yeah, that'd be absolutely fine.
Mm. Okay, so that still compiles. Let's make sure that I have added everything. No, I didn't. Alright, so this is going to be a bigger commit. There. So mission accomplished. We have our UART driver, we have our printf, we have assertions, we have a couple of string functions. It's all great. So next time, what would we do? We could start. Uh, we could start interrupts, I think, actually, because I wanted to work on them later, but it makes sense to have them early. So I think we're going to work on interrupts, but we can talk that. We can talk about that after the stream. Let's take a look at what you guys said. Cheers. Thanks for the answers. Yeah, sure, no problem. I'm still a little Bill trying to learn. Yeah, but it's Python you're learning. It's another world entirely. Um, it's a great world where you need more logic than low level skills. So I really like Python for that, honestly. The amount of available tools is so huge, so good. And with Python 3, um, they they went from having these interfaces that were either lists or iterators and both would work, but one had huge performance issues, the list, because you had to copy it all, and the iterator has functional issues because once consumed, it would not produce the same output. And in Python 3, they basically made everything iterators, and they added a list built-in function, and it's like very convenient and easy to think about it. It's an iterator. And if you want it to be a list, you call list, it's explicit. See the value of explicit programming again at work. Um, okay. So if you guys have questions, or you, Metal Snake 2, if you want us to discuss what you're going to do next, I don't know. We can do that off stream too. I don't have a preference. But yeah, I think working on interrupts would be a good thing to do.
Mm-hmm. That would make the UART also.
So yeah, we could complete your driver with that, but it's not really the point. The point would be to start thinking about the scheduler and threads.
Right. Okay.
So having a timer, having a timer with regular ticks, the really basic stuff, and scheduling threads. Starting to think about that.
Okay.
Python doesn't feel explicit at all. It's weakly typed, but it is explicit. You really get what you see. I don't understand. Like it's it's a criticism I made myself in the past, but by working more with it, I don't think it's true. It was true with Python 2, not Python 3. But that's my opinion, and I'm not Python expert again. Like I don't code in Python nearly as much as I could in C, so I can't like. It's just my opinion currently. All right. So it's 11. It's late enough. We're gonna stop the stream here. Thanks for watching. When will be streaming? When will we be streaming again, Metal Snake?
Um,
Next Tuesday?
for now, for now, I have a little bit of work going on
Okay.
next week as well. So uh, right now I'm aiming for Thursday. Might be sooner.
Thursday. Okay.
Thursday should be good.
No need to make it sooner.
Okay, then Thursday.
It's better that people know when to come. So
That's a
Thursday,
very good
next
point.
Thursday. Okay. So yeah, guys, thanks for watching. Have a good night. Enjoy life. You know, it's a weekend, and see you soon.
Good night.